measuring one port is nice, but most of the time you are interested in characterizing a two-port network, right? So, well, again, you have a big box, right, and then you have a nice looking screen, and then and then you basically have sources for two connectors. So, this is port 1 and port 2, and this costs a lot of money, right. So, now the question is and the idea is that you have an unknown two port, and you would like to measure its S parameters. We've already seen why it makes sense to measure S parameters rather than Y and Z. And so what do? You connect this guy using a cable to port 1, and you connect the second port to this box using cables. So, what do you think we should do now? What all challenges do you anticipate based on your experience with the one port network analyzer? What comment can we make regarding challenges with respect to the two port? The question I asked is what measurement challenges do you anticipate? Well, if you didn't know how the exact length and the Z naught of one cable, it's not very likely that when you have two cables you suddenly become wise, right. So, the properties of this cable are unknown, right. The properties of this guy are unknown. So, what you in effect have is you have an unknown two port this is cable 1, right, and then this is the device under test, this is unknown two port cable 2, and this is the VNA port 1, this is VNA port 2. All right. So, if you want to measure S parameters of the DUT, what all do you need inside the VNA? What must be there inside the box? Yes, Karthi, what do you think? We need a frequency, we need obviously a sine wave generator, right, if you wanted to make measurements fast, you probably need two of them, right, one pushing current into one exciting port 1 and the other one exciting port 2, or you finish making measurements at port 1 and then go to switch to port 2, what do you think? In other words, what you are measuring at port 1 will be you are measuring the transmitted and reflected waves at port 1, and likewise you are measuring the transmitted and reflected, the forward and the backward waves at port 2, and you can control which source you want to activate. So, for example, if you only activate the source at port 1 and you measure so in other words you push something here and you measure this and this, all right. What comment can you make about what all measurements will you be able to make with by measuring V1 minus and V2 minus? You will be able to obtain S11 and S and what? S11 and S21, right? And likewise, when you excite the source at port 2, you will get the other two parameters, right? Okay. So, but now we have, we have how many unknowns here? Well, we have 3 unknowns corresponding to the 2-port response of this cable, and here you have 3 unknowns with respect to the output cable, correct? So, what do you suggest we do? What do you suggest we do? 6 standard kind of standard devices. Pardon? Exactly. I mean, the straightforward. I mean, what you want to do is basically say get rid of the DUT. You replace. You calibrate. So you assume that the rest of the circuit doesn't exist. You put in the 3 standards here, right? Open, short, and 50 ohms, and from that you will be able to calculate these the properties of that unknown 2-port, and likewise you do the same thing here, and you will be able to get the properties of cable 2. Correct? Okay. Now, unfortunately, it turns out that that's not all. Okay. And what do you think might be another problem? No, that's all equivalent to, I mean, basically you are saying that the VNA port is not good, right? That's equivalent to adding an impedance here, which is equivalent to adding something to this unknown 2-port, which is going to get calibrated, correct? So it turns out that in reality, I mean, ideally, if the DUT was not there, right? Okay. What comment can you make about whatever S12 you measure or S21 you measure? Forget about calibrating, cable 1 and cable 2. Let's say without the DUT, we should expect S12 and S21 must be equal, and what must you expect that measurement to yield? What is S12 and in English what is S12 or S21? Pardon? Yeah, okay. So forward and I mean S12 is the effect of an excitation at port 2 on the response at port 1 and vice versa. So what do you expect to see ideally? The device under test is not there, I mean it's just been removed. I've removed there's nothing, man. Huh? No, I mean, looks like you guys don't understand the question, right? Yeah. All right. So what would you expect to see for S12 when you measure S12 and S21? Pardon? 0. Why is this so difficult? Is this clear or no? Somebody said S12 times S21. What? How did you get that? What connecting both? There is nothing in the middle. I mean, right? So ideally, if there's regardless of how bad the cables are, I mean, they are simply within quotes isolated from each other. The 2 ports are isolated, correct? So in principle, whatever you push into port 1 should have no effect on port 2 and vice versa. So ideally, without the DUT, you must expect S12 is equal to S21 equal to 0. But in practice, what happens is that there is always going to be some mechanism through which port 1 talks to port 2. It could be, direct feed through, right, so here is your okay. It turns out that there will be these two ports will talk to each other no matter what. Okay. I mean, this path ideally will be 0, but actually, remember that in the world, nothing that's supposed to be 0 will be 0, and nothing that's supposed to be infinite will be infinite, right? So here the S21 is supposed to be 0. In practice, this S21 and S12, even without the DUT, will be some small value. Okay. So in other words, what we have is basically another unknown 2 port okay, between these two. All right. So now you need to figure out basically what you're measuring at ports 1 and 2 are the DUT, but now you have something here and some port between the input and output. So this models a practical measurement scenario, right? If you remove the DUT, of course cable 1 and cable 2 will modify the what you're going to measure at the individual ports, and the 2 ports will have finite isolation, will not have ideally the isolation between the 2 ports must be infinity. In other words, when you take the log of the S12 or S21, you should get negative infinity dB, right? In practice, again it depends on frequency. At low frequencies, of course, everything is isolated, right? But as frequency becomes higher and higher, capacitive impedance becomes smaller, and between any 2 points there is some capacitance, and at sufficiently high frequency, the impedance of the capacitance keeps reducing. So as frequency keeps increasing, the isolation between 2 ports which are supposed to be isolated will not be infinite, and you can model that as an unknown 2 port in. All right. So what do you think we should do to fix this problem now? Okay, so there are many ways of doing this, each with progressively increasing complexities. One thing that he points out is that, well, the simplest thing to do is to say, well, I will first calibrate this 2 port, find this 2 port, right? But remember that finding, if you terminate this part with open, short and through and 50 ohms, you are not only getting information with regard to this 2 port, but also through this path, because port 1 and port 2 are talking to each other. But that path is actually, has hopefully a very small strength. So, the first cut approximation is to say, oh, well, when I am calibrating port 1, I assume that this path's gain is so small that it does not affect calibration of port 1, right. Similarly, with port 2, right. So as soon as I calibrate, these two ports, then I will remove the DUT is still not there, and then I will measure the S matrix of the ports without the DUT, correct, and that should give me what is happening with this, with the unknown port. Does it make sense, right? Okay. A more sophisticated way of saying this is clearly there is an error in this approach, in the sense that when you are calibrating the individual ports, you assume that the other port is not in the picture at all, right? That is clearly a problem, right? For most applications, for many low frequency applications with several gigahertz, this probably is okay, right? If you want to do a more thorough job, basically what you do is basically remove the DUT, and just like how we placed impedance standards, to measure or calibrate a one port, you now have to have a two port standard. Remember when we were calibrating a one port, we said we needed these impedance standards to be able to estimate what that unknown two port is. Now we need a two port calibration standard, and the standards that are typically used are basically what is called a through, which is something which is electrically very short. So this is basically for all practical purposes, this is measuring the S parameters when you short these two ports. Right? Okay. So then in other words, the Z DUT is simply replaced by a straight connection between the two ports. Okay. In other words, you can think of it as a transmission line with zero length, right? And the other one is a 50 ohm transmission line. So this is called a through. Okay, and the other one is a transmission line with a very well controlled characteristic impedance Z naught and a very well known time delay T, right. So these are additional calibration standards needed. Okay. So that you eliminate the effect of the second of the unknown two port, which basically exists between port 1 and port, right. So you make all these measurements, and then you put the DUT, and since you know all these, the rest of the, you know this, you know this, you know this, you will be able to go and figure out what the two port parameters of the DUT, all right. And several standards exist. As you can imagine, there are several calibration techniques with increasing complexity and therefore accuracy as you keep going, and they are all aimed at figuring out how to eliminate this unknown two port, and the calibration standards and the quality of the through and so on all start to matter, and these become very, very relevant only at very high frequencies. Again, the notion of high frequency is dependent on wavelength and the frequency of operation. All right. So with this, this basically, over the last lecture and this, we have covered the principles of vector network analysis. Vector network analysis itself is a huge area, right? People still keep writing papers about calibrating a vector network analyzer. And of course, with time, there is, as you can imagine, there's been a lot of progress in the way this calibration is done. Earlier, you would have to physically go and connect the cable to the open, the short, the load, and the through. And as you can imagine, people are not careful, and then they to connect the end of the cable to an impedance standard, some people would not tighten it all the way, right? Some people would over tighten it, and all sorts of errors, and then the calibration standards get spoiled. So now there's an electronic box which basically has switches inside and is computer controlled to basically go and change all that stuff, do all that stuff for you, right? So so this vector network analyzer, depending on the frequency of interest, is as I said, a very expensive instrument. And when I say very expensive, it can go to several crores without blinking an eye, right? And this is obviously a very specialized instrument which requires a lot of attention to high frequency detail, mechanical quality of build, and so on. And okay, so with this, all that I had to say on about distributed circuits and the VNA is done.